Hello, Tech-ni-shn here again. Today I'm going to look at the SI5351A VFO. I will check the output level, harmonics and the phase noise. The VFO I've used for testing is a design by CesarSound. An assembled version of it is available from eBay and AliExpress. It is commonly known as a 10 kHz to 220 meg VFO. The assembled version I have is slightly different to the CesarSound version, and code modifications are available on the web to correct some differences. The SI5351A has a nominal output impedance around 50 ohms. However, it is a CMOS device that is not designed to drive low impedances like 50 ohm mixers or attenuators. The data sheet specifically states a low capacitance to drive into, and additionally it also says that jitter is affected by the if you exceed the current settings of the device. The current setting, the jitter is directly transferable to phase noise. Getting back to the document, if you put a low impedance on the output, it takes it out of the limiting region and degrades the waveform. This affects both harmonic and spurious levels and also phase noise. If one is driving multiple outputs, it can intermodulate between the outputs due to excess current consumption. Another important note is that the SI5351A is DC coupled. I've seen a couple of circuits where blocking capacitors aren't used. Fortunately, this unit has a DC blocking capacitor, and the low order even harmonics are well suppressed. Some designs drive a logic gate which have a high impedance. The QRP Labs designs have this. In this assembly, I've put a 470 ohm and a 56 ohm internally on the output of the SI5351A. This acts as a moderate impedance load to the SI5351A and is also useful for driving a Class A MMIC. The output of this divider, when measured into a 50 ohm spectrum analyzer, is a nominal minus 10 dBm, and this has a variation of approximately plus or minus half a dB from 0.8 MHz to 220 MHz. I've used a MMIC of approximately 20 dB gain. On the output of the MMIC is a 3 to 5 dB attenuator, which is used to provide a good termination to the amplifier and also the mixer. Even if the output of the oscillator is a sine wave, the clipping action of a diode ring mixer will regenerate the odd order harmonics. The MMIC has to provide a nominal level of plus 10 to plus 12 dBm. So a MMIC capable of greater than plus 17 dBm and nominal 20 dB gain should be used. Suggested MMICs are a ERA-5 or a Galley-5. I also have some old Serenza NGA586 devices, and I'm using one of those. The equipment used is as before: spectrum analyzer made by Siglent, the SSA3021X, a 10 dB attenuator, also a 3 dB attenuator this time, a Rigol DG1062Z, and the HP8647. I'm using those to do comparison noise measurements. Also, miscellaneous coax cables and adapters. The crystal filter is one from mostly DIY RF, and it is set for approximately 2.7 kilohertz bandwidth. On the screen is the setup I'll be using to look at the output level and harmonics. I've gone from right to left this time instead of left to right. The SI5351A is driving into a MMIC using a ERA NGA586. On the output of the MMIC is a 3 dB attenuator, and this goes into the spectrum analyzer, and one can observe the output level and look at the harmonics. I'm only interested maybe up to 40 megahertz, but I'll set the spectrum analyzer to 100 megahertz. The setup shown on the screen is looking at the phase noise. The SI5351A VFO is on the left, then this enters into the MMIC amplifier and possibly a low pass filter and an external attenuator to set to plus 7 dBm. This enters the 10 dB attenuator. This is used to give the MMIC a good load, whether looking inside the bandwidth of the filter or also at when the generator is away from the center frequency. Additionally, the crystal filter also sees a good termination on its input. The crystal filter, as described before, is used to look at the noise plateau at 8.997 megahertz, and this enters the spectrum analyzer, which is also set to 8.997 megahertz, and the span is approximately 10 kilohertz. I've made some additional notes and I'll go over those, and it explains some of the other comments. This test method uses a crystal filter to suppress the carrier. This is so that the spectrum analyzer can make a measurement without being overdriven by the carrier. On the QRP Labs website, there is documentation on how this testing was done, and that is quite an interesting read. The oscillator noise generated by the SI5351A and also other oscillators is made up of both AM noise and phase noise, so this is a composite noise. The spectrum analyzer cannot differentiate between the AM noise or the phase noise using this method, so it's an umbrella measurement. It covers both of them. I was able to do some tests with a Tech-ni-shn Ultra, and though I got sort of measurements that were comparable, the levels seemed a bit off, so I'm not quite sure how the Tech-ni-shn Ultra responds to noise, but I will document. I've documented the method using the Signet SSA302NX. The testing of the phase noise was done at approximately 9 megahertz, and one can approximate the results for a higher frequency by adding 20 log over the to the ratio of the F high and F test So if one had 18 megs output instead of 9 megahertz, then 6 dB could be added to the phase noise testing. This is just an approximation though. So when I perform the tests, I use the spectrum analyzer to look at the carrier level with the oscillator set in the middle of the passband of the filter. And I note this down as level A. And then I adjust the SI5351A VFO for offsets 5, 10, 20, 50, 100 kilohertz, and that becomes level B. So by working out the difference between the A and B levels, then one gets a ratio of dBc per hertz. If there's a spurious in the measurement, I adjust the marker off slightly so it measures the noise plateau rather than a discrete spurious. Important thing to note, this testing shows at 1 hertz bandwidth. There's never a 1 hertz bandwidth receiver when you need it, but in real receiver where you've got 2.4, 2.5 kilohertz bandwidth for the SSB, then by taking 10 log of the bandwidth relative to 1 hertz, then one can work out the difference in the dB with respect to the bandwidth. And this is approximately 34 dB for a 2.5 kilohertz bandwidth. Also tested the Rigol DG1062Z and an old HP8467 at the test frequencies. This was tested without the ERA-5 MMIC, but it still had the 10 dB attenuator between the signal generator output and the crystal filter. If one tests the assembled receiver later, it's a 10 kilohertz spacing, then one can do what is called a reciprocal mixing test and a reciprocal oscillator test. And the results should be similar to the phase noise test with the bandwidth factor, the 34 dB added. We can test that later once the complete assembly is put together. A few more notes. The SI5351 has about 3.5 volts peak to peak unloaded. If we attenuate that using a divider of 470 ohm and a 56 ohm, the 56 ohm being in parallel with the load impedance of the MMIC, then about 175 millivolts peak to peak is available. This is approximately 62 millivolts RMS, which is approximately minus 10 dBm. If we assume that the composite phase noise or composite noise in a 1 hertz bandwidth is 140 dB below the minus 10, then that is minus 150 dBm. The 0 dB noise floor in a 1 hertz bandwidth is neg 174 dBm. This can be calculated from KTB, the K being Boltzmann's constant, T being temperature 25 degrees C, or in this case 17 degrees C, and B bandwidth, which in this case is 1 hertz. That gives you negative 174 dBm. If we add the noise figure of the MMIC, let's say 4 dB, then the noise floor on the input of the MMIC is neg 170 dBm. So there is about 20 dB difference between the MMIC noise floor and the SI5351 noise. So there shouldn't be any deterioration in the oscillator noise floor due to the use of the mimic. The minus 10 dBm should drive the mimic to about plus 10.5 dBm, and if we add 3 dB attenuator on the output, then this becomes plus 7.5 dBm, which is excellent for driving a plus 7 dBm type mixer. This is the first test setup. We are looking at the level of the fundamental of the SI5351A oscillator and amplifier. The level at 10 megs output is close to plus 10.6 dBm. This is at 10 megahertz. The third harmonic and fifth harmonic, seventh, ninth harmonic are there. Notice almost complete absence of the second, fourth, sixth, eighth, and additional even order harmonics. A square wave is made up of fundamental plus odd order harmonics. There should not be any even order harmonics present. If we change the frequency, the still very low levels of even order harmonics. The level is still approximately plus 10.6 dBm. If we go further up, the level is still approximately plus 10.5 dBm, so the output is very flat. One could use this into a attenuator to check receiver levels. I will now proceed to do the tests at for the phase noise. I have set the carrier to the approximate centre of the crystal filter passband. The level is approximately minus 1.7 dBm. The passband of the crystal filter will become apparent as I tune off the oscillator from the centre frequency. I'll activate the internal preamp and reduce the attenuation so one can see the noise. I'm 10 kilohertz away from the centre frequency, so if I go to amplitude and put the preamp on and change the input reference level to minus 50 dBm. I'll use some averaging on the trace to reduce the variations. Also, I'll activate the noise marker so we can read directly the noise in dBm per hertz. One can use the marker locations to change the positions of the marker to give a more average level. So this reading here at 10 kilohertz away is minus 137 dBm per hertz. If we change the oscillator for another 10 kilohertz step, we're now 20 kilohertz away, and if we average the display, slightly worse at minus 133. If we go out to 100 kilohertz away, for example, this is 100 kilohertz away, one can see the noise reduce even further. So this is approximately minus 142 dBm per hertz. There will be a slight adjustment to those levels as the input level to the spectrum analyzer with a signal in the centre of the pass band is approximately minus 1.8 dBm. So if we take that away from minus 144, it is approximately minus 122. I have previously taken results of this, and they'll be on the last page of the document, and I will present that after this part of the video. These are the results that I promised earlier. This is the composite noise tests at 8.997 megahertz with a crystal filter. On the first column is the frequency spacing from 8.997. The first four lines are 10, 20, 50 and 100 kilohertz below, and the second four lines are plus 10, 20, 50 and 100 kilohertz above. The first measurement, the second column, is the level of the noise with respect to minus 1.8 dBm, the output of the filter. I neglected to put in the 3 dB from the output of the amplifier, as the level was sufficiently low to go through the crystal filter. The levels 10 kilohertz away, if we go just on the first line, is minus 135 dB below, minus 135 dBm. If one corrects that for the minus 1.8 dBm that comes out of the crystal filter, the relative level is minus 133.2, 1.8 dB difference. If you move the spacing down to, say, 100 kilohertz away from the carrier, the noise is below 142 dB, which is a good result. And if you check on the other side of the carrier, you have similar results. If we go along to the DG1062Z made by Rigol, the results in the dBc per hertz column are very, very good. I've found out before from tests that it's quite good for this is a 14-bit DDS generator. There are 16-bit generators made by Segment, but I haven't tested one to see how good it is. And the HP5351A columns, this is I suppose what one would call a budget signal generator used for radio workshops. The phase noise isn't good, but it's very useful for doing signal to noise tests with deviation. It provides a stable carrier, but the phase noise is probably its weak point. So at 10 kilohertz away, it's approximately neg 105, neg 106 dBc per hertz. And it's quite usable for doing basic tests. As one moves away further from the carrier, the phase noise from the oscillator drops by more than 20 dB. And I expect if I went even further to maybe 200, 500 kilohertz or even 1 megahertz, then it would drop further again. These figures, remember, are dBc per hertz, and if you want to see what sort of levels they are in a SSB bandwidth, then one would add 34 dB to them, which is the 10 log times the ratio of the bandwidth relative to 1 hertz. So this is the end of the results of the tests, and I believe the SI5351 is quite a good result. And I have tested SI570 chips in the past, and they're close in. They're probably a little bit better than the SI5351, and further out they're probably just about match each other. So I have certainly no complaints in using an SI5351A, and we'll do some tests later on in the video series to see what the receiver has in terms of reciprocal mixing performance, and we'll go from there.